Thank you. All right. So, because of the quiz, we're not fully done with 11.2. So I'm gonna pad out that section a little bit. Does this limit exist? We're about to discuss how we can actually show how these two-dimensional limits can exist. Because they're very difficult. You have to show that it works for any path in which we approach the function. So that's proving to be difficult because there is theoretically an infinite amount of paths. So notice that direct substitution here leads to 0 over 0, which is not good. So then if you approach the function along the x-axis, you get that the above is 0, the bottom becomes x squared plus 0. We get 0. And let's say we approach it along the y-axis. We get the above is 0, bottom is here. So again, although you get two different paths to agree, we realize that that's not enough. Again, for just completion, I'll show another path. What about along the path of the parabola? Y is equal to, what am I saying here? Let's say we want to do it along y is equal to x squared. So this squared goes here. Our function. Okay, so this is where the y's become x squareds. And again, notice that this won't reduce any further. So this is why we try to invoke the Squeeze Theorem. Okay. Reminder of what the Squeeze Theorem said. It said, I won't draw the picture, but I'll write out the equation. If this is true, that's true, and the limit, as you know, this is the This is the one-dimensional version of it. It translates to the two-dimensional version of it. If the limits for this and that are the same, we may assert the limit sandwiched function, the squeezed function, is indeed the same. So let's apply that idea to this function here. Function, what was it, xy squared over x squared plus y squared, I believe. Oh, the squared is on the x. Okay, so the way we're going to invoke the squeeze theorem here is we're going to figure out how far away is this surface to the origin. Okay, and just like absolute value tells you the distance from the origin on the real line, the same can be thought of as the absolute value of this function minus the origin, which is just this function. When you square something, it's always positive, and the sum of squares is always positive. That's why you get this result. Okay. So then you notice that notes. This is true. That x squared is less than or equal to x squared plus y squared, where equality holds if y is equal to 0. Okay. You can divide both sides by this quantity to achieve something like here. Notice that I could have also said that x squared ranges between 0 and x squared plus y squared. So I can divide the inequality here to get this. Okay. Why am I doing this? Well, I'm trying to build this function here. So I can now multiply this whole thing by the absolute value of y. And we're hoping to use the squeeze theorem. Because look, actually the squeeze theorem could even have had this. So we're trying to use this over here. It's starting to happen because we get this. Right? Because 1 times anything is that thing. So we can now say, oh, instead of f of x, we have f of xy. Instead of g of x, we have g of xy. Instead of h of x, we have h of xy in multivariable functions. And so they have multivariable limits. We can say, okay, notice that the limit as xy approaches 0, 0 of 0 is 0 because the limit of a constant is a constant. Furthermore, notice that the limit as xy approaches 0, 0 of our h of xy is just absolute value 0, which is 0. Notice that we have found through that analysis, the inequality analysis we did earlier, that those two functions indeed sandwich this function in the middle, which is our desired function of analysis. So by the squeeze theorem, I get that the limit as xy approaches 0, 0 of x squared y over x squared plus y squared is indeed equal to 0. So now we actually showed it. We actually showed it using the theorem. This is why mathematics is powerful. When we prove theorems, we then don't have to check an infinite number of things. The theorem did it for us. We proved it irrefutably. So the real beauty in this structure is how to prove the squeeze theorem, how to justify the squeeze theorem truly holds. We're not doing that in this class, but you can do that in real analysis. So I encourage all of you guys to go take real analysis. Hopefully I can teach it. But Dr. Zola will do a great job of teaching that. I also encourage all of you guys to go major in physics. Seriously. Do it. Okay. Now let's talk about continuity. These are really important, and I just couldn't gloss over them. Continuity. Okay. Nuity. Okay. When you have dyslexia, the letters start messing with you. So you got to make sure you did it right. I didn't even know I had dyslexia until like a few months ago. Until someone told me, hey, I think you have it because you're flipping things. Function of two variables is called continuous at AB. So if the limits of x, y approaches a b of f of x, y is equal to f of a, b. And so the function is continuous on a subset of R if for every point on that subset of R, the function is continuous. So this is continuous at a point. You can be continuous on a whole subset of R. And as a matter of fact, for our multivariable functions here, our subset D of R2. So, I'll leave it to you guys to go find out why polynomials are continuous. Because we have a lot to talk about in the partial derivatives chapter. As you guys saw, I already uploaded the homework for partial derivatives. There's a lot of homework problems because this is a very important section. Partial derivatives are very important. And now we're starting to get into real calculus, real calc 3. This has always been real calc 3, but it's starting to really rev up. Okay. So I leave it up to you guys to review continuity and discontinuity in the chapter. It's very important. I don't have time to go over it in class, but it is very important. So don't gloss over that. Hopefully I have definitely assigned homework problems that have to do with the continuity concept. So that's really important. So I don't have time to really go into it in detail today because quizzes always do that to us. So let's talk about 11.3. Derivatives. Dyslexia does not give you an excuse for poor spelling. Okay, so if I have a multivariable function f of x, y, all right, I define f of x, y. This is defined as the partial x, the partial derivative with respect to x of f of x, y. What is that partial x you're talking about? Okay, so remember we had a function f of x. Okay, let's say it equals to some y. Then I took dx of f of x, which is equal to f prime of x, which is dy dx, which is equal to y prime. Okay, Capital D dx just means total derivative. We called it the derivative, but now in order to create a distinction between capital D dx and partial, these are deltas, so partial x. So d dx, capital D dx versus partial x. This is a total derivative, meaning it's a derivative in one variable and one variable only. Partial x is the same. It is actually a derivative in one variable only. However, it's dealing with a multivariable function, meaning when I take partial x of f of xy, I treat everything that is a constant as a constant and every variable y as a constant. And I only treat x as the variable, but that means actually there is a f of y of xy, which is defined as partial y of f of xy. Okay, what does all this stuff mean? The book goes into limit definitions, and that's very, very important. I'm not going to cover that right now. Okay. Well, let's just do some examples. Let's say my function f of x, y is equal to 3x to the fourth plus 2x squared y squared minus 3y cubed. Let's calculate f of x, y. This is equal to partial x of this polynomial, multivariable polynomial. Okay. This partial x, just like d dx, is a linear operator, meaning that it travels to each of these terms. I will show it once and I'll never show it again. But it travels to each of these terms. I'll show this once and then I'll never show it again. It's just implied. So let us take our first partial derivatives in here. It's not that scary. It's just like total derivatives. This expression only has x. So it's as if we're taking a total derivative. We ignore the 3 and we just take the derivative of x to the fourth, which is what? 3 times 4x cubed is what results. Because you bring down the 4, you subtract 1 from the 4, it becomes a 3. Here's where now it's starting to get different than before. Here, partial x sees as 2x squared y squared. It thinks y squared is the same thing as a 2. It's just a constant. It's going to ignore it. And so this just becomes 4xy squared. And then minus, what do you think partial x of 3y cubed will be?
3y cubed?
Pardon me?
Doesn't it just stay the same?
But no, it's a constant.
Oh,
Oh,
right. 3 is a constant. Y cubed, for partial x's concern, to partial x, 3 is a constant, y cubed is a constant, and it's a multiplication of constants, which is a constant. So the partial x believes that this is just a constant, and it tells you that that's 0. So this is the new thing about this thing. This is the new partial derivative rules. So this becomes 12x cubed plus 4xy squared. This is what my f of x of xy is. So that's the partial derivative with respect to x of our function f of xy. What is the partial derivative with respect to y? Again, just like last time, the partial y travels across each term. It's a linear operator. When it hits this term, what does it equal? Yes, because it's got a constant and only x is in it. Partial y treats that like a constant altogether. What happens when it hits this term? Correct. It ignores the x squared and the 2 completely. It differentiates y squared to 2y. And when you take the product of 2y and 2x squared, you get 4y x squared. What happens when it hits this guy?
Yes, 9y squared.
Yes. And so our result is that this is it. So that's how you take partial derivatives. Let's do some more examples. Let's do another example. What is f sub x of y? F sub x of xy is partial x of cosine of x squared plus y squared. Okay. Derivative of cosine. Partial derivatives behave just like total derivatives in that sense that they utilize the chain rule. So then, what's partial x of x squared plus y squared? Pardon me?
2x.
Yes, because when it hits this term, it becomes a 2x. When it hits that term, it's just a 0. So it's 2x plus 0, which is just 2x. So this becomes negative 2x sine of x squared plus y squared. All right, so what's s of y? That's y. That's partial y of cosine of x squared plus y squared. Derivative of cosine is what? Gives me what? What does partial y think this whole term is equal to?
Y squared. Or 2y, sorry.
2y, because x squared, it just perceives that as a constant. And y squared, once it takes the derivative of that, becomes 2y. Okay, now you know how to take partial derivatives. Quotient rule, chain rule, product rule, that all applies to partial derivatives. Now, let's evaluate given find okay, all that means is take the partial derivative with respect to x, take the partial derivative with respect to y. Once you're done, evaluate the function at these values. Let's do it. Okay, this becomes a 3y x squared minus, that just becomes partial x, so it's just a 2y. Partial x of this is nothing. So this implies partial derivative with respect to x of this function is 3 pi x squared minus 2y. So evaluating it at 1, 0 gives me 3 pi times 1 squared minus 2 times a 0, which just gives me 3 pi. Let's take the partial derivative with respect to y. When it hits this term, everything is just constant to it. It becomes 0. When it hits this term, it ignores the 2, it ignores the x, it takes the derivative of the y, just leaving the constant part, this negative 2xy, this negative 2x, I mean. Then when it sees the 3y squared, it thinks it's 3 times 2 times y once it takes the derivative. So then this equals negative 2x plus 6y is our, then we evaluate it, 1, 0, we get now we've calculated away. It's time to think about the interpretation of these values. What is this negative 2 and this 3 pi really? Well, don't forget we're in Calc 3. We're in Calc 3. So a function f of x, y defines a surface in 3 dimensions. Does it not? And along this surface, we can have any kind of curve C, okay? Some curve C that is on the surface, it's riding the surface. We can find some, like a level curve, if you will. It's kind of like a level curve, it's not, yeah, actually it is a level curve, right? Okay, so notice that at this curve C, it's like a line. So we can find a tangent line to it in the direction of y. Notice that this is x, this is y, this is z. Here's a tangent line, tangent line, t, let's say y, for C. Notice that we can also find a tangent line at this point right here. Oh, I'll just move the point. I can't move the line, I'll move the point. We can find it in the direction of x, like your t, x. Notice at this point, P can have value A, B for x and y, and then some C. So P is equal to some A, B, C, okay? So at that point, P has a tangent line going along the y, has a tangent line going along the x. Where's the tangent line going along the z? Well, we don't have one. Why? This is a 2-dimensional surface. It should be able to be parametrized by x and y only. It's a 2D surface. To create a 3D surface, you would need the parameterization to be in the x, y, and the z. But we only have a 2-dimensional surface, so we don't need a tangent line in the direction of z. So notice that the slope of the tangent line in the direction of x and y correspondingly Can you guys see that? Can you see that, Ivor? I feel like that's really hard to read that. looking at the video, writing it in blue. I'm going to rewrite this. T of x is a line, right? So it's going to have associated slope. Whatever the output of f sub x evaluated at AB is, will be the slope of this tx. Remember, derivatives give you slopes. That's their, so this is telling you the derivative in the direction of x. And t of y will do the same thing for, it will give you a slope. So this thing. Okay? That is the interpretation for partial derivatives. It just extends the derivative idea to two dimensions. I don't need to review the derivative idea, but I will real quick. Remember, you had some curve. Here's some point on your curve. Here's my f of x. Here's some tangent line, t. Y, any line is equal to mx plus b, right? Well, calculus shows you that f prime, let's say this is some point A. F prime of A is equal to this m of that slope of that tangent line. Right? That's what calculus taught you. So, extending this out into, put a z-axis in there, you're going to get the same thing, just a little different. Now you have derivatives along your other variable axis. Yeah, I figured, because the blue color on this, the only time I'm probably going to get away with being able to use this blue and that green is if I do something like that. If I do something like this. That's probably the only thing that's noticeable if I do it like that. So I'll keep that in mind. So that's the interpretation. We did some calculations. We did calculations, interpretations. What else is there left? Implicit differentiation. Aha! Okay, so remember back in the day in Calc 1 when we did implicit differentiation? When all of us really, when we all learned Calc 1 and we talked about implicit differentiation, none of us really know what the heck is going on. We're like, okay, you want me to do this? I need to do this to pass this class. I need to do this to get this problem right. Sure, I'll do it. But really, the concept behind implicit differentiation is the fact that we can't solve for y completely in a function. Solving for y in this situation right? And when you get y is equal to plus or minus square root of 25 minus x squared, you get two functions. You get the positive and the negative. And when you superimpose them on the graph, you notice that it disobeys the vertical line test, meaning it's no longer a function. So you say, oh, how would I take a derivative of this? You say, well, I can say that my y is my function, some function purely in x, so that this function transforms to this. And then I can take d dx of this function. So across some domain in which it's defined, I can take I can do implicit differentiation. Remember how we did implicit differentiation here? So let's say take the total derivative d dx of both sides. D dx hits 2x, it thinks that becomes a d dx is x squared, it becomes a 2x. D dx hits this y squared. You guys remember what happens here? You take the derivative of it normally as if it was a variable, as if it was a function in x, right? And then you said that's dy dx, didn't you? You did, didn't you? And then you said, okay, d dx of 25 just becomes 0. Why are you doing this? This was always weird to me. I never really understood why this was happening. It's a consequence of this right here. It's a consequence of saying, okay, let's represent the variable y as a function of purely an x. That's why we can even take the derivative of it with respect to x. So when I take d dx of y squared, I'm really taking d dx of f of x squared, right? What I'm saying is d dx of y squared is the same thing as d dx of my f of x quantity squared. Notice that that's very simply 2 f of x times d dx of f of x, right? By the chain rule. So this becomes 2 f of x, f prime of x. But this is the same thing as 2y, y prime, which is 2y dy dx. That's why you do that weird stuff. And then, we solved for dy dx and the problem was over. You end up getting y prime, which is dy dx is negative x over y. So let us do implicit differentiation for our multivariable functions now. Hopefully that has elucidated what was going on in Calc 1. Notice that, had I defined it like this, okay, this function right here is defined in 3 variables. What we want to find is partial z, partial x, and partial z, partial y. So what's going to have to happen is z is going to have to define as my f of x, y. Just like y had to be defined as your f of x. Now y gets demoted, z gets promoted, and now that y goes in and put a comma. If somehow we went to 4 dimensions, then we would have something like this. If somehow we went to 5th dimensions, then we have something like this. You get the idea. Okay. So let's do impartial implicit differentiation. So let's take partial x of this whole thing. Partial x of 1 is just 0. Partial x of x cubed is 3x squared. Partial x of y cubed is 0. Now, what is the partial x of z cubed? You must recall that z is really secretly a function in the variables x and y. So partial x of z cubed can't just equal 0, because z secretly has variables of x and y in it. So, right, it becomes this, but then we're doing implicit differentiation, right? So notice that partial x of z here, depending on your x and y, you have to do the chain rule, right? It's not very obvious with the way I've written it out that the chain rule applies, but applying the chain rule, you get this, right? Where that partial x represents the derivative of the inside function. Now comes this stuff. And I won't do that right away, because that's going to require some thinking. Let's write down what we have so far. What is partial x of 6xyz? All right. Notice that 6x, oh wait, no. Okay, the only thing that can be ignored is this 6. So what ends up happening is you're going to have to take the product rule here, because z is a function of x and y. Okay? So what you're going to have to do is you're going to say, all right, well, what happens when I get partial x of 6x y times z plus partial x of z times 6x y. Does that kind of make sense? It's the product rule. Remember when we did like f of x times g of x? This equals our h of x. Then h prime of x was equal to f prime of x times g of x plus g prime of x times f of x. You guys remember the product rule? Yeah. So what we have now is a product rule and 3 variables. So this reduces to 3. Let's move over here. This reduces to 3x squared plus 3z squared partial z partial x. Plus, now that we've like thought it through, this part is easy. Partial x of this thing is just 6y times your z. Partial x of this thing, well, partial x of z on its own, z is really that. So partial z partial x is equal to partial x of xy, which is equal to this. We may denote it as this. I just rewrote some of my put back here. This becomes 6yz plus 6xy partial z x. Everything is equal to 0. What am I doing over here? Why did I write that here? Okay, I was writing it up here. Okay, 6xy partial z partial x is equal to 0. Okay, so in order to stop confusing myself, I'll work from left to right here. And I'll erase the board. So just like last time with dy dx or y prime, what we do want to solve for is partial z partial x, because that was what we were aspiring to find in the problem. So we send this term and that term packing. So I get partial z partial x when I factor it out. This is 6xy plus this 3z squared. That's equal to a negative 3x squared minus a 6yz, right? So partial z partial x is equal to negative 3x squared minus 6yz all over 6xy plus 3z squared. Notice that I can factor out 3. From the numerator and the denominator. Which implies that partial z partial x is equal to negative x squared plus 2yz over 2xy plus z squared. That's implicit differentiation in a multivariable function. So then let's find partial z partial y. And recall that that means I take partial y of x cubed plus y cubed plus z cubed plus 6xyz is equal to 1. So when it hits this term, it becomes a 0. When it hits this term, it becomes a 3y squared. When it hits this term, again, z is a function of x and y, so this becomes 3z squared partial z partial y. When it hits this term, we have to do the product rule. So it becomes partial y of 6xy times my z plus partial y of z times 6xy. All this equals 0. So this becomes a 3y squared plus 3z squared partial z partial y plus, okay, this thing just thinks this becomes a 6x times z. And this thing thinks, oh, this becomes a 6xy partial z partial y. Bringing the calculation over here, factoring out a partial z partial y. Adding the other terms over to this side, I get this becomes a negative 6x z minus the 3y squared. Factoring out the terms here, I get 6xy plus 3z squared. Divide both sides by that. This term in the parentheses. Again, we may factor out a 3 from the numerator and denominator. So I get negative 2xz minus y squared over 2xy plus z squared. Implicit differentiation in multiple variables. Now, what if I have a function what is these guys? Let's go. Partial x of xy is just y. Partial x thinks ln of z is just a constant. Partial y of xy, it perceives that that's just x. Partial y perceives ln of z as just a constant. So this one's going to be interesting. It's just going to ignore the e to the xy. It thinks it's a constant. So it's going to take partial ln of z with respect to z. This becomes 1 over z. Right? Partial z of ln of z is 1 over z times the derivative of the inside, which in this case is trivial. Partial z of z is just 1. So then this reduces to at least I got that one in. Let's see. Then there's higher order partial derivatives. And there's Clairaut's theorem. So I'll probably address a little bit of that next class before I move on. Then there's Laplace's equation, the wave equation, harmonic solutions. Woo!
Did you see this?
What is that?
Do you get the emails from feedback?
About the mask stuff?
Yeah, you